Hi everyone, welcome back. We're in Python here. If you remember in the last video, we went over our dimensional analysis for our problem, and we found that the Reynolds number, the Schmidt number, and the Sherwood number all describe our problem as dimensionless numbers. And at the end here, I kind of went over how there's a relationship between the two, and we will be simulating like a data collection process, and we're going to use linear and nonlinear regression to actually figure out what this A, B, and C are. So we're actually going to do this in Python. And what we want to do first is we're going to be importing NumPy, which is numerical Python. And this is just a library of functions that we're going to be using in some of our code. So for this simulation of our experiment, what we want is we want 100 Reynolds numbers, and to do that, we're going to create an array here, which is going to have random numbers, 100 random numbers, uniform. And when we do this here, this random uniform, it's going to pick, well, we need to input a minimum, a maximum, and then how many numbers we want. And what this random uniform does is it just picks however many numbers we put. We're going to use 100. It's going to give us 100 random numbers, with each number having an equal chance of being picked, I guess. For our Reynolds numbers, it looks like our low end is at 2,000, our high end is 35,000. So we're going to use that in our code. So we have 2,000, 35,000, and we want 100 numbers. So if we take a look at that, it gives us 100 random numbers here, all in an array, and they're just in between 2,000 and 35,000. So this is our simulated data of Reynolds numbers. We're going to do the same thing for the Schmidt number. So again, random, uniform. Now for these, it's going to be between 0.6 and 2.5. And again, we want 100 numbers. And if we take a look at that, again, we have 100 numbers here, and they're all in between 0.6 and 2.5. So this is our, for our experiment, our Reynolds number and our Schmidt number. Now for the Sherwood number, the way we're going to do this is we're going to take a look at this up here, which is the relationship between the Reynolds number and the Schmidt numbers, to where we have 0.023 times the Reynolds number raised to the power of 0.83 times the Schmidt number raised to the power of 0.44. This is the relationship found experimentally. So we're going to use this, 0.023. We're going to use this to calculate what our Sherwood numbers should be if the experiment was 100% perfect. 0.83 times the Schmidt number raised to the power of 0.44. Check that real quick to make sure it's right. Okay. So if we take a look at that, these are our calculated Sherwood numbers. This is the data we would get if the experiment was perfect and there was no error present at all, which of course is impossible, really. There's always going to be error. So the way we're going to handle this is we're going to add our own error into the Sherwood number calculations. So we're going to use a function in Python, which is kind of like the random uniform numbers we got above. But instead of uniform, we're going to use random normal. And what this does is we need to input this LOC right here, which is this is going to be the center of the distribution, or the mean. And then we have our scale here, which is going to be our, let's see here, our standard deviation. So, for example, 10 and 1, it's going to give us a number. The mean is 10 and the standard deviation is 1. So we get 11. Makes sense. We get 9.3, and if we just keep running this, it's going to give us a random number each time. Another thing we can do with this is we can actually put in an array into the input for the mean. So instead of just putting 10, we can do 10, 20, and 100, for example. And still with a standard deviation of 1, what it's going to do is it's going to give numbers back. That here's a number with the mean of 10 and a standard deviation of 1, which is 7. We get 18 for the 20, and we get 99.9 for the 100. And again, you can run it, and you'll keep getting different numbers. It's just randomized. So the way that we're going to use this to, I guess, introduce error into our data is, instead of using an array of like 10, 20, 100, we're going to use this array of Sherwood numbers. So this is an array here, Sherwood numbers. Now these are the ideal Sherwood numbers that we would get if the experiment was perfect. And for the error, we want to introduce about 10% error. So what we're going to do is, for the standard deviation, we're just going to take the Sherwood number and we're going to multiply it by 10%. So that's going to give us, it's going to take every Sherwood number and it's going to basically introduce about 10% error into the number. So here we have an array, and these numbers all have a little bit of error in each one. Okay, so this is our data. Now what we want to do is we want to take the data and we want to do a linear regression on it. So for linear regression, I'm going to go into here. The first part of linear regression is going to be, we want to make the equation look something like this. Y equals mx plus b. Because it's a lot simpler to do a linear regression and more possible to do a linear regression if we have stuff being added rather than everything being multiplied and raised to powers. So the way we're going to do this is we're going to use natural logs. So we're going to take the natural log of the Sherwood number equals natural log of a plus b times the natural log of the Reynolds number plus c times the natural log of the Schmidt number. So this is what we're going to use for our linear regression. Now linear regression is done with matrices. So what we're going to do we're going to take a matrix here, and it's going to have the Reynolds numbers here, the Schmidt numbers here, well, natural log. And in here, it's just going to have 1. And then we're going to have another matrix here, this is going to have natural log of A, B, and C. So this is our answers. This is what we're trying to solve for. This right here, this is just ones, and so on. This right here is data that we actually collect. This is our collected data. And in Python, we use the random uniform distribution to get this information. And then this equals right here an array, and this is going to be the natural log of the Sherwood numbers. So the way that this actually works is that we're trying to isolate this right here. So we're going to call this array X. We're going to call this array, we'll call it B, and we're going to call this Y. So what we're going to do is we're going to multiply both sides by the transpose of this X array. So we'll do this over here. So we're going to have an array that's like this. The transpose like that. We have array B. We have the transpose again, and then here we have Y. Now, the next thing that we're going to do is, in order to get rid of this transpose of X times X, we're going to multiply by the inverse. So we have this right here times X, and that's the inverse, times transpose times X times B equals the inverse of these right here times the transpose times Y. And since we multiplied by the transpose, we did this on purpose because this will create the identity matrix, which is just like multiplying by 1. So what we're left with is this cancels out. We're just left with B on this side, and that's our answer. So B equals this. And that's the idea behind linear regression, more or less. So we're going to be doing this in Python. And what we want to do is we want to create an array called X. And we kind of said this here already. X is going to be an array of ones, natural log of the Reynolds number, natural log of the Schmidt number. So I believe it's column stack. Is that a thing? Well, I guess we'll find out. We're going to do, in order to get 100 ones, we're going to use a function called ones like, oh, here it is. Ones like Sherwood number, because there's 100 Sherwood numbers, so it's going to give us, oh, let's see here. Is it array? There we go. It was a underscore. Okay, so one's like Sherwood number. It's going to take an array that is the same dimensions as the Sherwood number, and it's going to replace everything with a 1. So that's what it would look like. Then we're going to take the natural log of the Reynolds number and the natural log of the Schmidt number. What did I do? Let's see, column stack. An array. All of them must have the same first dimension, a sequence of arrays. Okay. Okay. So, oh, we will try and add in some parentheses. Maybe that will help. No. We'll take a look here. NP column stack A, B. I'm not exactly sure why it doesn't like this. Unless they're all not. We'll get rid of that. Leave a parenthesis at the end there, maybe that was the problem. Get rid of that. Get rid of that. Get rid of that. The 3 were given. Okay, that doesn't help. Gives, takes one positional argument. np.column stack. np. Huh, that is interesting. Why is it not working? Leave 100, 100, make sure that they all have the same dimensions. Take a look at this here. Is that our problem? np.log. It's probably a very simple problem. Most of the time it is. We have the Schmidt number. Maybe it wants... No. What we'll try is... We'll just try to put brackets there. Oh, okay. Yep, it wanted brackets. So there we go. Apparently brackets was the solution. I guess that makes sense. So now what we have here is a bunch of arrays where we have one array, which is made up of three separate arrays. But we have in the first position here, we have ones. In the second position, we have the natural log of our Reynolds numbers, and in the third position, we have the natural log of our Schmidt numbers. And if we look back here, that's kind of what this should look like, with ones, natural log of the Reynolds number, natural log of the Schmidt number. Okay, so that is good. Next thing we want is, we want to take what we have here, and we want to type this into Python, where we're looking for b, which is an array, which is the inverse of the transpose of x times the transpose of x times y. So we're going to put this into Python. And the way that we're going to do this is we're going to need the inverse. np dot, I believe it's linear algebra. Maybe we'll see if it pops up here. Inverse. Is that correct? Linear algebra. Well, here's what we can do. We can do numpy linear algebra inverse, and we'll just see how we do this. Linear algebra dot inv. That seems to be, yeah, okay. Yeah, that's pretty simple. So dot inv, this is going to give us the inverse of x, array x times, and the way we do array multiplication in Python is with an @ sign. And then the way we do the transpose is dot t. So this is the inverse of array x multiplied by the transpose of array x. And then we're going to multiply that by the transpose multiplied by array y. If we remember, array y is the natural log of the Sherwood number. So we're going to take the natural log of the Sherwood number, and hopefully it runs. Let's see here. What is the problem? I see. What is the problem? Maybe this one's parentheses. No. Let's see. Input operand 1 has a mismatch in its core dimensions. Maybe we'll just run everything. No. What's the issue? What's the issue? Oh. maybe, actually. There we go. Okay, so something important to keep in mind when you're doing matrix multiplication is that the commutative property, I believe, does not apply. So this times, I'm going to use at because that's what we use in Python. That times that does not equal that. Oh, that's bad. Times that. I had them backwards and the dimensions didn't add up. Because when you're doing matrix multiplications, the dimensions do matter. And I had it backwards, so the dimensions weren't adding up. And that's the problem that we had there. So go ahead and run everything. We are getting the exact numbers, which we introduced about 10% error, so we shouldn't be getting the exact numbers. So we'll look up here and see what happened. Or we're going to set this error to be the new Sherwood numbers. Okay. Now we have the Sherwood numbers. Now we have the Sherwood numbers, but we actually have the error this time. Okay, so yeah, there we go. So 0.81 instead of 0.83, 0.41 instead of 0.44. This is -3. The reason why we have -3 is because remember that we use the natural log of a where is it? Right here, this is the natural log of a. So -3 is the natural log of a. So in order to get a by itself, we're going to have to use the exponential. And that's going to be b. And it's going to be the first index, or it's going to be the 0th index, which is the first number. Okay, yeah, there we go. Okay, so here we go. So this just gave us b back again. This is our matrix of the correct answers, and then I took the e to the power of this -3, 0.57, and it's over here. So we have about 0.81, 0.41, and 0.028, which is decently close to our perfect solution up here. And of course the error comes from the error that we added ourselves. So this is our answer right here. Now, this is linear regression. So now I want to talk a little bit about nonlinear regression. The way that nonlinear regression works is that it is going to look at, well, let's see here. If we have a graph, and again we have Sherwood number equals a times the Reynolds number raised to a b times the Schmidt number raised to some c. What it's going to do is it's going to look at each of these separately. So let's say our Sherwood numbers look like this, and from our right-hand side of the equation, based on our a, b, and c, we'll use red for this, our numbers look like this. Basically, what we're trying to do here is we're trying to choose a, b, and c in such a way that the distance between all of these is as low as possible. We're trying to minimize the distance between these. So instead of being a linear algebra problem using matrices, this is going to be a minimization problem, which is more of a calculus thing. So that's what we're trying to do. We're trying to choose A, B, and C such that this red line, this red distance, is as low as possible. And this is called, we're taking the sum of we're taking the squares of all of these. Because if we didn't, this would be considered, since this red is below the line, this is going to be a negative distance, a negative distance, a positive distance, a positive distance, a positive distance, and a negative distance. So some of these negatives would cancel out with the positives, and we wouldn't get an accurate answer. So when we square it, it makes everything become positive. So that's kind of the sum square part. So we're just going to be looking at the difference between this over here and this over here, and trying to choose A, B, and C such that the difference is minimized, or the difference squared is minimized. So to do this in Python, we're going to be using the minimization function. So we're going to have to go back up here, and I believe we're taking this from SciPy, the optimization functions. Import minimize. Okay, we'll run this. We'll just run everything. So minimize. Okay, so for this minimization, it's going to take in a fun, which is function. Let's see, function. It's the function that we're trying to minimize. And then it's going to take in this x naught here, which is our initial guesses. So we're going to need to have initial guesses. We're going to need a function to minimize and initial guesses. So I'm going to define a function called sum. We'll just do sum s, or sum square. We'll call it sum sq sum square. And it's going to take in a p, which is going to be an array. And this, we're going to need to return the sum, so dot sum of our equation here. Now the cool thing about nonlinear regression is that we can keep the equation looking like this with the exponents, or we can make it look like this with the natural logs. We can do both. It doesn't matter. I'm going to keep it in this form. So here we're going to have our a. So that's going to be in array p, it's going to be the first number, which is going to be the 0th index, times the Reynolds number raised to the second number, which is the first index, times the Schmidt number raised to the power of the third number, which is the second index. Okay, so we have this here. Now this is our modeled value. We need to subtract, or we need to subtract that from the actual value. So that's going to be the Sherwood number minus this squared. And we're going to minimize sum squared. We're going to need initial guesses, and for that I'm going to choose values that are nearby. So 0.02, 0.75, 0.35. Those are just nearby. And let's see what we have here. We have an array. So we have about 0.05, 0.76, and 0.1. These look a little bit too far away, which means I might have done this incorrectly. So we're taking the sum of the difference here. Yeah, that should be around 0.4. Maybe this didn't go correctly. We'll do that. See if that fixes it. This is a lot. Oh, okay. This is a lot better. So we have about 0.02, 0.83, 0.84 ish, 0.5. Okay, that's a lot better. So I'm gonna go ahead and run all of this again. Okay. So actually, every time I run this, it regenerates these Sherwood numbers and these Reynolds numbers and the Schmidt numbers, which gives us a different set of data. So it's going to give us different calculated A, B, and C's. So what we're left with is, with our linear regression, we get about 0.26, 0.82, 0.42, and with our nonlinear regression, we get about 0.032, 0.8, which is pretty close to our 0.81, and 0.43, which is decently close. Now, a lot of the differences in this data comes from the error that we put in here. So again, if I run everything again, then we have about 0.02, 0.02, that's a lot closer, 0.82, 0.82, 0.83, closer to 0.83, and then 0.45, 0.42. So it's pretty close, which is pretty fascinating to me, that we can use nonlinear regression through matrices, and we can use linear regression, which is through the matrices, and nonlinear regression, which is basically a calculus problem of minimization, and we're getting nearly the same answer. So I'm going to go ahead and just do it one more time. And again, every time I run this, it's giving me different data. So yeah, we can see down here that now we're getting 0.015, which is pretty far away. And again, it's due to this this 10% error, roughly 10% error. It's possible that it's more than 10%. Yeah, we're getting 0.017. So you can really just run this and you'll get a different answer every time. 0.022, 0.018, 0.84, 0.85, 0.44, 0.47. So this is our regression. So these are the coefficients A, B, and C that we found through linear regression and through nonlinear regression down here. So in the next video, we're actually going to use Python to graph all of this. And we're going to draw a 3D graph, and we're going to plot our data, and we're going to plot our model based on these A, B, and C's that we found using our regression. So thank you for watching, and I'll see you in the next video.